Yeah, go ahead. Okay, so we have a question here about the homework. Go ahead.
Yeah, so because you have to you decide you look at the one on top of you, and you look at the one on top of you over j minus weight of I. How do we calculate weight of I?
Oh, that's given as part of the input, right? So the input file contains.
But we don't know which I's are
There. Well, I forget what is this. This 5 is the number of elements. W is the overall weight capacity. 10 is the overall weight capacity. And then you have, I think that these are the weights, and then these are the values.
Is it, do people have unique, the weights have unique values?
Not necessarily, no.
So, because weight of I means
The weight of the ith element, right? So
okay.
produce the optimal, let's see, the third value. So these are the weights, these are the values, right? So given this is an input to the 0, 1 knapsack. So in this case, n is equal to 5, right? And so you have items A1, A2, A3, A4, and A5. Right? Your overall weight capacity is 10. Those are the first two lines. And then your weights, Wi, W1 is equal to 3, W2 is equal to 2, W3 is equal to 5, 4, and 7.
Okay. And V of I.
Yeah, V1 is 10, V2 is 4, etc. Right. That's what the input is. Right. Isn't that the exact same as homework 2? Yeah, you just use your parser from homework 2. Yeah. Okay. Any other questions? Yeah, go ahead.
We can use the actual knapsack algorithm we use from that assignment too, right?
It's not going to be possible. You'll need to use the dynamic programming solution. Yeah, but I mean, the dynamic programming solution should be easier to implement than homework 2. Right. Okay. All right, so today we're going to finish up with giving you the Church-Turing thesis. Right? Remember that we started this all with the statement, is this true? Can algorithms solve any problem? Right? And to do that, we needed the language in order to express that. Turing machines decide languages. We covered what languages are. We've now covered what Turing machines are. So what does it mean for a Turing machine to decide a language? Okay, and that's a very simple definition, right? A Turing machine decides a language L if and only if, 1, it halts on all inputs, right? If you write a program and it results in an infinite loop, right? Most of the times you don't want that to happen. Of course, you want poll loops sometimes, like an operating system or a game loop or something that continues until some external action kills it or something. A Turing machine is similar. You want it to be a finite expression, a finite program that actually executes and terminates at some point. Furthermore, it accepts or rejects if and only if X is in the language or X is not in the language, respectively. Right? So when it halts and accepts, then that defines. It will only do that for strings that are in the language. It will halt and reject only for strings that are not in the language. Okay. The key there is that a Turing machine really only decides a language if it halts on all inputs. If it goes off into an infinite loop, it is not deciding any language at all. Right? So the original questions begs the question here: are Turing machines what we mean by computers? And is that what we mean by algorithms? That's the Church-Turing thesis, right? The above is the Church-Turing, two people, Church-Turing thesis, right? So Church, Alan Church, I think. No, it's Alan Turing and something Church. I don't know what his name was. But anyway, it's a thesis because it's not a theorem. We're just going to accept that that's what we mean by algorithms. Because if you come up with a C program, I can come up with an equivalent Turing machine program. If you come up with a Java program, I can translate that into a Turing machine language. For any Turing machine that I build, you can write a Python program that does the exact same thing, right? That is a non-trivial proof. But that's what we mean when a programming language is called Turing complete. A programming language is Turing complete if it can express any program that if it can express any a program that that can if it can express a program for any Turing machine. Turing machine, right? Not necessarily those ones that go off to infinity, but that is also true. You can write an infinite loop, right? You've all done so by accident, probably at one point, right? So the real question is, can a Turing machine, or is there a Turing machine? Is there a Turing machine, or TM for short, that can decide, or for any language, for any and all possible languages, right? In other words, if I come up with a language, is there guaranteed to be a Turing machine that decides that language? Likewise, for every Turing machine that decides one language, right? If and only if, basically, right? And the answer is going to be a clear no, right? There are problems that have no algorithmic solutions. That's one way of looking at it. There are languages that are not decidable by any Turing machine, TM for short. Right? I'm going to show you two proofs today. The first proof is based on Cantor's diagonalization technique. For that, we need to see his original diagonalization technique because everybody in here on Wednesday said that they'd never seen it before. So first of all, we're going to need some definitions, right? An infinite set is countable if its elements can be enumerated. Enumerated without missing any. All right. For example, n is clearly countable. The natural numbers. 0, 1, 2, 3, ... I can enumerate them. I can put them into an order, and I'm not going to miss any of them. All right. Suppose that I missed one. 1 billion. No, it's at the 1 billion in first place. Right? I'm not going to miss anybody. I can do the same thing with z. Right? Now, I can't write it two-way infinite. That would not be a list. I have to start somewhere and go only one way. That's easy. 0, 1, negative 1. 2, negative 2. 3, negative 3, ... Okay? So I'm not going to miss any of those guys. Q. The set of all rational numbers, a, b, such that a and b are integers, and b is not 0 because, of course, you cannot divide by 0. I'll show you how to do this. Right? So all you need to do is write them in a big, giant tableau, like we've been doing here. Right? 0, actually, 0 will be by itself. We won't worry about that. 0, 1, 2, 3, 4, ... off to infinity. Yeah, go ahead.
When is the term tableau used instead of table? You just want to be fancy?
Yeah, you want to be fancy. Exactly.
Is it French or something?
I'm sure it's French. Yeah, it's a tableau. Right? So, what is my enumeration? It's 1 over 1, 1/2, 1/3, 1/4, 1/5, ... Right? Down here, I will have 2 over 1, 2 over 2. So I'm going to end up repeating a lot of things, right? 2 over 4. 1/2 is repeated twice, right here and right here. 1 is repeated twice. All right? It's going to be repeated actually an infinite number of times, but it won't matter. Right? all I need to do is make sure that I have an enumeration. And so here's my enumeration, right? If I just go to start reading them left to right, right, I'm never going to get to the second row. If I go in one column, I'm never going to get to the second column. Yeah, go ahead.
So should you also do 1, negative 1, 2, 3?
Yeah, I mean, the same trick as here for the negatives, right? All you need to do is list a number, then immediately list its negative, right? And then 0, that's what gets us started. So here is my enumeration. Go across the diagonal. Right? And every time you do, come back down over here and go on the next diagonal. Now, am I going to miss anybody? Nope. I'll repeat a lot of people, but I don't need an efficient enumeration. There is an enumeration with respect to the prime decomposition of numbers. I just need to show you that this is countable. So these are all countable sets. Countable. Now what about the real numbers? Reals. Okay, all real numbers. Cantor came along about 150 years ago and said, not all infinities are equal. That some infinities are more infinity than others, right? And so what he pointed out was that R is not countable. And even at the time, his proof technique, it's called a non-constructive proof. His proof technique was not even accepted by people like, I think, Fermat, who rejected it. And said this is a new kind of math, and it's icky, and it's weird, and I don't understand it, so therefore I'm going to reject it. But 150 years later, everybody accepts this, okay? So it's not countable. Here's my proof. Here's Cantor's proof, I should say. By way of contradiction, suppose that they are countable. Suppose, say, 0 to 1 is countable. Right? All I have to do is show a small section of the numbers is not countable, and the entire thing is not countable. Okay? Well, to be countable means that you can put things into an order. This means that there's an order, x1, x2, x3, ... These are the numbers in 0, 1. If you want to, you can take care of 0 and 1 right away and just list them out. It doesn't matter, okay? Now what I'm going to do is I'm going to write them all down. So I'm going to write them vertically here instead. x1, x2, x3, x4, ... Right? That's an enumeration that I suppose that exists because I'm assuming that the real numbers are countable. Now write out the digits. Because they're between 0 and 1, you can go ahead and go 0 point. And I'll call these digits D11, D12, D13, D14, ... off to infinity. D21, D22, D23, D24, ... off to infinity. And likewise. D31, D32, D33, D34, D41, D42, D43, and D44, ... off to infinity in both directions. Now, I'm not going to be able to, zigzag like I was over here, right? With the rational numbers. But what I'm going to do is I'm going to formulate a new number, right? Create a new real number, y. Right? The way that I'm going to do that is I'm going to take each digit on each row and I'm going to disagree with it. Right? This is where Cantor's diagonalization comes into play. I'm going to go along this diagonal right here. And what I'm going to do is I'm going to create a new number that is D11 minus 1. Right? So here, let me give myself some more room here. right? 0.d11 minus 1, d22 minus 1, dot, 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 off to infinity. I should just move this down here, right? d33 minus 1, right? Now, the convention here is if it's 0, if the digit is 0, then I'll just wrap around to 9, right? 0 will go to 9, right? d44 minus 1, dot, dot, dot. Now, tell me about y, right? Where is it in this enumeration right here? It's not. Why not? Y is not equal to x of I for any I. Why? Because x of i's jth digit, or ith digit I should say, ith digit disagrees with x of i's ith digit. Why? Because of the way I constructed it.
Why is there
Sorry, yes, you're right. Sorry. Y's, come on. Y's ith digit disagrees with xi's ith digit, right? There we go. Right. Why? Because of the way that I diagonalized away from it, right? So, does such an enumeration exist? It can't. I necessarily missed one, right? I necessarily missed y, right? So, there's an entire hierarchy of infinities. I think that he's also given credit for the infinite hierarchies. This is a stylized n. It's in the Hebrew alphabet. It's Aleph, right? Aleph null and Aleph. It's like a weird n. Aleph 1. This is countable sets, such as the natural numbers, z, and even the rational numbers, q. These are uncountable sets. For example, the reals and the complex numbers, right? You can go with an infinite hierarchy, a countably infinite hierarchy of infinities, 2, right? So, Aleph 3, right? Dot, 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 right? So you have not just one infinity, but you have an infinite number of infinities, right? Each one of these is provably larger than the previous infinity, right? Why? Because of Counter's diagonalization technique. One way that you can build the real numbers is by taking the power set of integers. Well, then how do you build an LF2 set? You take the power set of reals. How do you build an LF3 set? You take the power set of some LF2 set, right? And you just keep going as many times as you want. So there's Cantor's diagonalization technique in a nutshell, right? I just gave you the 5-minute version of maybe a 45-minute talk on Dedekind cuts and all that kind of crap, right? All right, so I'm going to use that technique to show the following theorem. There are, or I should say, the set of all Turing machines, TMs, is countable. 1. 2, the set of all languages is uncountable. 3, therefore, there are languages such that no Turing machine decides them. Right? Because of this Cantor's diagonalization technique from over 150 years ago. Okay? So let's show number 1 first. The set of all Turing machines is countable. Remind me, what is a Turing machine? Let's go over here to, where's my computability? Should be in computability. It's a 7 tuple, right? All right. What does it look like? this is the version I want. There's a Turing machine, right? All it is a table of transitions, right? What could you do to that table? Fact. You can encode a Turing machine in binary, right? In other words, you can look at this. The encoding of a Turing machine, where M is some Turing machine. Do you buy that? Why? Well, you've got a set of, what is it? It's a graph. What did we start out by showing you how to do? Encoding a graph in binary, right? What's another way of looking at this? Any program can, in fact, all programs are, be encoded in binary. Take a C program, compile it. What's the result? Machine code. What is machine code? A bunch of zeros and ones, right? So in other words, Turing machines are strings. And what have we already seen about strings? Strings are countable. Why? Because I can put them into an enumeration, ... right? Likewise, Turing machines can be put into an enumeration. Suppose that I've got machine 1, machine 2, machine 3, ... off to infinity. All I need to do is encode them as a string, and they appear somewhere in this infinite sequence. Some of them probably like 0. That's not a valid machine. That's not enough information to actually, like if you compiled something to one single bit, that's not going to be runnable on any machine at all, right? So some of these are not going to be valid Turing machines, but the valid Turing machines, they are going to be in a countable enumeration. So it's enough to just talk about the machines themselves. Oops. 2, 3, ... There's my enumeration. Right? So, oops. Number 1, I think we buy it. Right? Number 2, the set of all languages is uncountable. For a proof of that, all you simply have to do is do the same Cantor's diagonalization proof. By way of contradiction, assume languages are countable. In other words, there exists an enumeration. There exists an enumeration. And I'll just label it as L1, L2, L3, ... off to infinity. There's my enumeration. Now, we have two facts here. One is that strings are countable, and 2 is that languages are countable. Okay? So what I'm going to do is I'm going to write both of these enumerations down. Right? X1, these are going to be, no, I'll go S. S1, S2, S3, S4, ... And this is going to be strings, which are countable. And now what I'm going to do is I'm going to write down L1, L2, L3, L4, ... These are languages, which by way of contradiction, I am assuming are countable, and therefore this enumeration exists. Now what I'm going to do is I'm going to put zeros and ones in here. 0, 1, 1, 0, ... 1, 1, 0. It doesn't really matter what they are. I'm just giving you as an example here. Now let me generalize this. This will be, I don't know, R sub 3, 3, or generally, it's going to be R sub I. Right? Result. Right? Where R sub I, J is going to be equal to 0 if X sub I is in language J, or if it's not in there, excuse me. And it's 1 if x of I is in language L sub j. Sorry, yes. I keep switching back and forth. I should do x, but I want to emphasize that they're strings, not numbers. Thank you. All right. So in other words, S1 is not in language, the first language. S2 is in the second language. It is in the third language. It's not in the fourth language. Now what I'm going to do is diagonalize away from it. 1, 2, 3, dot, 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 R sub I. And I'm going to create a brand new language, L prime. It's going to be all strings S, I, such that S sub I is not in L J. Right? Right? In other words, all I'm going to do is take this value here and flip it. So S1 is not in language 1, so I'm going to make it 1 into that language. It is in L2. S2 is in L2, so I'm going to make it not in the language. All right. So let me rewrite this such that. Well, yeah, that's what I want. Except that I don't want J, I want I, because I'm going along the diagonal. There we go. That was the difference. Right? So now my observation is the same as Cantor's diagonalization technique, where that L sub I is not equal to any language L sub I for any I. Right? Why? Because L sub I disagrees with L sub I in string S sub I. Right? So therefore, contradiction, no such enumeration exists. And therefore, the set of languages is not countable. Right? We know that the set of strings is countable because I was able to prove that by just writing them out. So therefore, there must be a Turing machine. There must be a language for which no Turing machine exists, because one of these sets is countable, right? And one of these sets is not countable. So provably, there are more languages than there are Turing machines to decide them. Right? That's a simple proof, 150 years old, but it's kind of unsatisfying, right? I'm just saying that there is some language, not that that language is all that interesting. Right? Yeah.
So L prime is this language.
That's I diagonalized a language, just like I created a number y, so that it disagreed with everything in my enumeration. This disagrees with everything in the enumeration as well. Right? Therefore, this is a language that has no Turing machine that decides it. Right? What is the language? I don't know. So let me give you an actual language. All right? We know that Turing machines are encodable as strings. So what I'm going to do is I'm going to have a language called the halting language, or the halting problem. And I'm going to define that as all pairs of Turing machines M and X. I'm going to encode those together such that M is a Turing machine that halts on X. Right? In other words, M on X, right? M is a machine, we run it on input X, and it will halt. All right? This is actually a very, very useful language. Why? What if your compiler could tell you whether or not, when it compiles, it'll give you warnings like, you have a function, a non-void function that doesn't return anything. Warning, that you need to write something to a return statement. you've added an integer to a double and then put that into a double, you have a loss of precision because of integer truncation. Warning, right? You can do all of these things, and a compiler can detect all that stuff. But can a compiler also tell you, hey, you're compiling a program that's going to result in an infinite loop? Have you ever seen that kind of error message before from a compiler? Nope. Well, why? Because it doesn't exist, right? L on halt is undecidable, right? In other words, there is no Turing machine that can decide L halt. There's no Turing machine that can look at another Turing machine and an integer, an input X, and say, when you run this machine on X, it's going to halt. Accept, reject, I don't care. I'm just going to tell you that there's no infinite loop. Right? So what I'm telling you is that there is no Turing machine to decide this. Here's my proof. By way of contradiction, again, this is still kind of non-constructive, but it's also a little bit trippy because it now gets into recursion, right? By way of contradiction, suppose that there is a Turing machine called H, right? That H exists to solve, that is, decide the halting problem. This language right here, right? L halt. Right? In other words, what H does is as follows. H on input M and X, it looks at this input and it will output halts and outputs 1 if M on X halts. 1 being true, right? It accepts the language, right? Or it accepts that string, excuse me. It halts and outputs 0, false, if M on X does not halt. In other words, it says, if you run M on X, it's going to result in an infinite loop. Don't try it, right? It's going to say it's not going to halt, okay? Now what we're going to do is we're going to run a machine on itself, meaning like the following, M on M, right? Does that make any sense to anybody? No? Why not? Why not? All right, so an operating system, right? What does an operating system do? It runs other programs. Hey, operating system, here's a program. Go ahead and run it for me. Right? What does a processor do? Processor is a program that it's a hardware program that runs other programs. I just put together a new MAME cabinet. But what is MAME? Does everybody know? Nobody knows MAME? Oh, come on, man. MAME? MAME. Multiple Arcade Machine Emulator. Right? It's how you can play old classic arcade games? You've never, no? Well, no, it's just a piece of software that you download, and any arcade game that has ever been made, you can play it. Right? How do you play old Nintendo games? Game Boy? How do you play old Game Boy games? Nintendo. Nobody's ever played around with emulators? You only what? Retro emulators? No? How else are you going to play old games like this? Right? Or RetroPie? That's what I actually put together. I got an Arduino no, Raspberry Pi, sorry. And I installed RetroPie, and in this little tiny box, you've now got millions and millions of games, right? Nobody's ever done that before? Y'all just play AAA modern games, right? Oh, come on. Say what? Oh, yeah, I'm sure. Yeah, there are Wii emulators. I don't know. My gaming stopped at Super Nintendo, basically. Wii emulators. Right?
Retro to us means cool math games.
Top 10 Wii emulators. There are at least 10 to even make this list, right? So,
Okay, we actually
well, there Dolphin looks like its number one is Dolphin. So you can go play old Wii games, right? Or I'm not sure how it works. Nintendo is notorious for having weird input devices, but I'm sure that it works somehow. Yeah, it's like arcade games that have weird input devices, like entire driving setups or whatever. Those are very, very difficult to play on MAME, but you can do it. Right? Oh, there's a whole culture of like old Reddit arcade, right? Arcade, get it? And cabinet. No, nobody has their MAME. Okay, MAME cabinet. Right. And you know, you can buy kits to do it, or you can build your own, or whatever. It's a whole hobbyist, isn't it? Nobody's ever heard of it.
you can play any arcade game.
Yeah. I mean, all this is you building this oversized classic MAME cabinet, and then all that's inside of it is a little tiny Raspberry Pi, and of course the screen. Right? And then there are purists that say, no, you have to get an old CRT monitor, or it doesn't count, or whatever. Anyway, can you run a machine on itself? Yeah, right? That's what most programs are. Programs just run other programs. You can have you can have entire operating system emulators. Wine, right, is a Windows emulator that can be run on Linux. Modern computing is all cloud computing, right? What are you doing? A Docker instance or a virtual machine. You are running 100 different operating systems on one piece of hardware, right? So it makes sense that you can feed a program into another program, right? I.e. M on M. Oops. Yeah, go ahead.
Can you do it like on Excel?
Yeah, why not?
You can run a virtual machine
Why not?
on a virtual
Yeah, you can do it many times as you want, right? These are just strings, right?
Well, people just don't do that.
Yeah, I mean, if you ran Windows on Windows, or if you ran Microsoft Word on Microsoft Word, what would happen? It would try to open up Microsoft Word, the executable, as a document, and it would be just a bunch of garbage that you wouldn't read, but you could do it, right? So you could still do this, right? It's not that weird, okay? Now what we're going to do is we're going to construct another machine, Q, right? That takes only a single input, an encoding of a machine M. And what we're going to do is we're going to halt or go into an infinite loop, depending on the answer that H gives us. H on M, M. If that says halt, right, then we're going, or it does not halt, then we're going to halt. If H on M, M says that it does halt, we're going to intentionally go into an infinite loop. Now, can we write such a machine? Yes. All we need to do is on input M, right? All we're going to do is run H on M, M, right? If H answers 0, right, false, then we're going to halt and output, I don't know, output accept. Right. Else, we're just going to go into a while one loop, and that's it, right? Anybody could do that in any language. Right? So yes, we can write Q. Now our final step, run Q on itself, as we said. Right? Does this halt? Does it halt or not? Right? Okay. Well, think about this. Q on Q halts if and only if what? What's the definition of Q? Q on Q will halt if and only if H on Q says 0. H on Q is 0. Right? In other words, if and only if Q on Q halts. Or, sorry, does not halt. All right. Yeah, go ahead.
So H on, so Q is just combined two.
Here's my machine. Here's what it does. Here's its implementation. Now take that machine and feed it into itself.
Oh, that's QQ.
Yep, that's going to be QQ. Q on Q. Now, Q on Q halts if and only if the halting problem, that other machine that we supposed exists, says that it does not halt. So Q on Q halts if and only if Q on Q does not halt. What do we have here? It's a contradiction. And what did our proof start out with? Yep, here we go. Right. By way of contradiction, suppose that H does exist. If H exists, I can construct another machine such that this contradiction occurs. Right. So therefore, H, that machine, H does not exist. Therefore, the halting problem is undecidable. In other words, there is no compiler for any language that can take any input and any program and say, that's going to be an infinite loop. Right? You can write some code, you can write a smart compiler that will say, I can simulate this for a little bit and I can detect an infinite loop, right? If I look at all the state in my program, right, and I keep track of every single state that occurs, and I ever go back to an original state, 100%, right, then of course you can detect an infinite loop. But for all inputs, for all programs, it can't do it. Right? There is at least one program and at least one input, as we've demonstrated with this proof, that there is no such detection software. And this was just the first one. This is what Turing showed. Turing showed that the machines that he envisioned are actually limited. That no, there's not an algorithmic solution. This goes all the way back to Gödel's incompleteness theorem, which really threw people for a loop because he showed that there are mathematical statements for which there are no proofs, or that the proofs are independent of your axiom set. So depending on the assumptions that you start with in your mathematical system, you can prove one thing is true. If you change the axioms that you start with, you can prove that that same thing is false. It's independent of these two things. Right? So there are, just like this, there are programs that have no, or there are problems that have no algorithmic solution. This is one of them. This is a concrete example. Basically, any non-trivial property of a language is undecidable, right? And you can use the same proof using reductions, basically. And that's what we'll talk about after the break. I'm just kind of disappointed that nobody knows anything about emulators. No? What are the? I built my own cab. I don't have any picture of it, but What it was
Your own what?
cabinet, cab. All right, Japanese.
Those things you were using
Cabinet.
online and
It was like the guess video arcade. What was it called? It was based on. Yeah, these things. What was this called? No, those are Neo Geo ones. Dang it. It's more like. It was more there. What's that one? Sit down style cabinets. I built one that that was kind of like this, right? And for many years, I just had a regular old desktop in it, and then that died several years ago. And so, about a year ago, I finally put together RetroPie, and man, has it been up to, like RetroPie easy install. It runs, I think, Ubuntu, Unix or Linux, and it has a really nice front end for all of the emulators. And I bought a bunch of controllers, classic NES controllers and stuff. Oh yeah, I do that. I do have that too. But when you're playing an old Nintendo game, you don't want a joystick, right? You want the classic D-pad or whatever it's called. Right? Man.
Doesn't a Nintendo game hook up to your TV, like an old TV?
Yeah, the old console.
We can do that on the.
Well, you have to do that. There's probably very few working Nintendo consoles out there anymore. Yeah, Game Boy Advance. There you go. Game Boy Color.
What's the game that we play with that dad? Like there's two guys with red pants and then blue pants.
Red pants, blue pants, karate. Konami Warriors, or Ikari Warriors. Ikari Warriors. That one?
No, it's like 2D.
Well, yeah. This is an overhead scrolling, infinite scroll up.
No, you go from left to right.
Oh, I have no idea then. Sorry. All right. Well, you need to use your break to check out some of the emulators that are available, right? And then join the UNL Game Dev Club.